Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 7th, 2025, just 2 days ago. It introduces a new deep learning system that makes adding complex features incredibly simple, requiring only about 10 lines of code for major changes that take thousands elsewhere. The paper is titled AXLearn, Modular Large Model Training on Heterogeneous Infrastructure, 2507.05411v1, and the implications for model training are quite significant. This system is designed for flexible, high-performance training across different hardware, like GPUs and TPUs. To illustrate this point, the first figure shows just how modular the system is. On top, we see a standard transformer model's components, all in red. Below that, we see how to add a complex feature called a mixture of experts, or MOE. A mixture of experts layer uses multiple smaller specialized networks and a gating mechanism to choose the best one for the job. The key takeaway here is that all the original red components are reused. A developer only needs to define the new green parts, the MOE layer itself, to create a much more complex model. Building on that idea of modularity, this next table really puts AXLearn into context. It compares AXLearn against other major deep learning systems like DeepSpeed and PyTorch FSDP. The columns check for key features, like being model agnostic, meaning it works with any model type, and supporting different hardware. What really stands out is that AXLearn is the only system listed that ticks every single box. It's fully modular and, crucially, runs on GPUs, TPUs, and also AWS Trainium, a combination no other framework on this list achieves. Okay, so this next figure gives us a look under the hood at how AXLearn actually works. The blue boxes here represent the core system. A developer starts with a simple script, and the JX Train composer handles the heavy lifting, things like parallel strategy and rematerialization, which is a clever memory-saving technique. It then generates a program for JAX, a high-performance library, which is compiled and run on the hardware cluster. The runtime then manages everything, including monitoring and fault tolerance, which is the system's ability to recover from errors, ensuring stability. This next table provides some hard numbers to back up those architectural claims. It introduces a metric called low-C complexity, which is a way to measure how many lines of code you have to change to add a new feature. We see comparisons for adding things like rotary position embeddings, or ROPE, a technique for helping models understand word order, and the mixture of experts we discussed before. The results are dramatic. Other systems have a complexity that grows with the model, requiring hundreds or even thousands of code changes. AXLearn has constant complexity, requiring 0 changes. So that constant complexity is great for developers, but how does it perform? This table benchmarks AXLearn against other systems on different models and hardware. A key metric here is model flop utilization, or MFU, which basically measures how efficiently the hardware is being used. Higher is better. Across Llama 2 models on GPUs, TPUs, and AWS Trainium, AXLearn is consistently a top performer. It often has the best model flop utilization and throughput, and it's the only system shown to run on all 3 hardware types, which really underscores its flexibility. So to wrap things up, this paper makes a really strong case for AXLearn. The 2 big takeaways for me are its incredible modularity, which we saw with that constant lines of code complexity, and its impressive competitive performance across different types of hardware. It really seems to be a system that balances developer-friendly design with state-of-the-art results on GPUs, TPUs, and even new hardware like AWS Trainium. This approach tackles some major pain points in large-scale AI development. That's all for this week. Thanks for tuning into the AI Research Roundup. I'm Alex.